Hello.
Hello.
Yeah, can you hear me?
Yes.
Okay, so today we'll cover the topic of the Chinese remainder theorem. So this is
Okay.
a very useful concept. It helps us solve problems involving congruences. So, for example, we'll start off with a couple of examples and then we'll look at the general process. So, let's say we have this question. We have to solve the system of congruences. Solve the system of congruences. X is congruent to 1 mod 3 and X is congruent to 4 mod 5 and X is congruent to 6 mod 7. So we have to find X which satisfies all three congruences.
hmm
Okay, so in such a problem, we can use Chinese remainder theorem. So before we look at the theorem, we'll understand the process, how to apply it or what can we do here. So without
Okay.
knowledge of the theorem, how can we do it? So in any congruence system like this, you can start off with the largest modulus. So here, this is the third one, which is the largest modulus, right?
Yeah.
We can say X is congruent to 6 mod 7.
hmm
Therefore, X will be equal to some 7k plus 6, right?
Yeah.
X will be some 7k plus 6. Now, use that expression and put that in the second largest modulus. So, we have something like this. So 7k plus 6 should be congruent to 4 mod 5, right?
Right.
Should be congruent to 4 mod 5. Now, if you think about it from here, can we say something about k from here, right? So if you think of the number 7k plus 6 is congruent to 4 mod 5. So you can say that 6, when you do mod 5, it will be 1, right? Right?
Yeah.
So this will be 4 mod 5, 7k plus, this is same as this, right?
Yeah.
So 7k will be congruent to 3 mod 5, right?
Oh, right. Yeah.
We want to say what is k? K is congruent to what mod 5? That's what we want to say, right?
Yeah.
So suppose we have 7k here. So 3 mod 5 you can write as, remember the 3 can be written as 8, can be written as 13, 18, 23, 28, right?
Yeah.
3 mod 5 is same as 28 mod 5, right?
Right.
So we'll write 28 mod 5 instead here. And now notice, why did I do that? Because I want to cancel 7, right?
Yes.
So I made a 28 which is divisible by 7. And now I realize that I can actually divide by a modulus on both, divide by a number on both sides as long as the thing that I'm dividing is co-prime with 5. So usually we have seen this, right? We have
Yeah.
seen A mod C. Now we can write it as AK congruent to BK mod C. This is totally fine.
Right. Yeah.
You can multiply both sides of a congruence by the same constant, but usually it is not allowed to divide, go the other way. Okay.
Okay.
If you divide it, you can get into trouble. There can be mistakes, but it is allowed to divide as long as K and C have GCD of 1.
Yes.
Do you understand what I'm saying?
Yes.
the thing that you want to divide on both sides should be co-prime with the modulus n or c or whatever. So here, if I have 7k congruent to 28 mod 5, I know 7 and 5 are co-prime with respect to each other, so I can divide. We are getting
Yeah.
k is congruent to 4 mod 5, right?
Yes.
Okay, so what have I done so far? I started with the highest modulus. From there, I got x is 7k plus 6. I put that in the second one. From there, I tried to solve for k in terms of mod 5. And I figured out that it is 4 mod 5, right?
Yeah.
So therefore, x will be 5k plus 4 or 5j plus 4 if you want. 5j plus 4, right?
Yeah.
And we'll put that in the last remaining modulus now, right?
Yeah.
So one second, let me just think. See, k was 4 mod. Okay, I'm making a mistake because k was 4 mod 5. So k is 4, 5j plus 4, right?
Yeah.
So k is 5j plus 4. So x is what? X would be, x was earlier 7k plus 6, right?
Yes.
So it will be
So
7 times 5j plus 4 plus 6, right?
yeah. So yeah.
So 35j plus 34,
Right.
right?
Mm-hmm.
We have used all the information we knew so far and we got x as 35j plus 34, right?
Yes.
We'll put that now in this one. X is congruent to 1 mod 3, okay? So
Yeah.
we'll say 35j plus 34 is congruent to 1 mod 3. Okay. So
Mm-hmm.
we are getting 35j plus 33 is congruent to 0 mod 3.
Yeah.
And 33 is anyway 0 mod 3. So
Right.
you can say 35j is congruent to 0 mod 3.
Right.
Right?
Yeah.
So from there, that means J should be 0 mod 3, right? Because 35 is not divisible by 3.
Yeah.
So we are getting J is divisible by 0 mod 3. So J can be written as some 35m. No,
Yes.
3m. What am I saying? J will be written as some 3m.
Oh, right, right, right. Yeah.
And earlier we had x as 35j plus 34, right?
Mm-hmm.
We had gotten that from the previous two congruences, right?
Yes.
Now I'll put j is equal to 3m. It will be 105m plus 34, right?
Yeah.
And now notice that this means that it is when x is divided by 105, x will be congruent to 34 mod 105, right?
Right.
Because x is coming as 105 times m plus 34.
Yeah.
So this by division algorithm, it means that if you divide by 105, you'll get 34 remainder, right?
Yeah.
So this becomes your answer for the overall system of congruences.
Yes.
So the system of congruences, if you recall, was 1 mod 3, 4 mod 5, and 6 mod 7. 1 mod 3, 4 mod 5, and 6 mod 7. And notice that the final modulus is coming as 3 into 5 into 7.
Right.
Do you understand what I'm saying?
Yeah.
Okay, so let's apply this process once more to a separate example and see if you are getting the right set of answers. Okay, so let's say we have x is congruent to 5 mod 6 and x is congruent to 3 mod 8. Try to work it out by the same method that we learned.
Okay. Wait, so I got 8k is congruent to 2 mod 6, but then I can't divide by 8 because they're not relatively prime.
So, 1 second. Uh, so, you have the problem is the 6 and 8 have a common divisor of 2, right?
Yeah.
Uh, so if you get x is equal to 8k plus 3, right?
Yes.
Then that you are putting it in the second one, right?
Right.
So x is equal to 8k plus 3. If we put in the second one, we are getting 8k plus 3 is congruent to 5 mod 6. And we are getting 8k is congruent to 2 mod 6, right?
Yeah.
So here, uh, think about it. What does it actually mean? This means that 8k is equal to 6j plus 2, right?
Yeah.
So notice that you can cancel, in this equation, you can cancel 2, right?
Right. Okay.
So you can say 4k is congruent, is equal to 3j plus 1, right?
Yeah.
So notice that this equation actually means that in terms of congruences, it means 4k is congruent to 1 mod 3, right?
Yes.
So that also tells us that there is a way to divide even if they don't have GCD 1, right?
Yes.
Because from here, by correct statements, we have gotten to here, right?
Right.
So the way to divide is if you have AC is equal to BC mod N, right? You want to divide by C, but it seems like C and N have some common factors, right?
Yeah.
So what we will do here is uh, this is going to be equivalent to A is congruent to B mod of N by, I think it is GCD of N and C.
Okay.
So here GCD of 2 and 6 is 2 only, right?
Yeah.
And notice that it became 6 by 2, it became 3.
Right.
So even if you can't directly divide, you can obviously write this equation, right?
Yes.
And from there you can cancel 2. So we are getting 4k is congruent to 1 mod 3, right?
Yes.
Correct. Now
Yeah.
this 1 mod 3, you can write 4k is congruent to 4 mod 3.
Hmm.
because 1 mod 3 is same as 4 mod 3.
Yeah.
And 4 and 3 have no common factors. So now I can say k is congruent to 1 mod 3, right?
Yes.
So we are getting k is congruent to 1 mod 3. So k will be equal to 3j plus 1.
Hmm.
And we'll put that in this, right?
Right.
So x will be equal to 24j plus 8 plus 11, right?
Yes.
So x is congruent to 11 mod 24, right?
Yeah.
So 11 mod 24 should be our answer. Yeah, that is the answer. Do you understand what is happening?
Yes.
Okay. So one more problem we can look at. Let's say we have to solve the system x is congruent to 1 mod 5, 2 mod 6, and 3 mod 7. Finally, you should be getting 206 mod 210.
Wait, I got one sec.
Hmm. You start with the highest one, right?
Yeah,
Did you get, when
I
you put
got
7k plus 3 into the second one, you should get k is equal to 6j plus 5. And then x is 42j plus 38.
yeah, I got that. But then for the last one, I got J is equal to 4 mod 5, so J is equal to like 5y plus 4, and then I put that in.
You have to put that in, x is equal to 42j plus 38, right?
Yeah, and then I got 210y plus 200.
4 times 42 plus 38 is not that, no? If you put 5y plus 4 times 142 is 168. 168 plus 38 is 206, no?
But you have to add the 4 at the end, right?
You have x is equal to 42j plus 38, right?
Yeah, and then you have J is equal to 5y plus 4.
Do the calculations. 42 into 5y plus 4 plus 38. What is this? It will be 210y plus 206.
Oh, when I was doing my math, I wrote 6 and it looked like a 0. Okay, yeah, it's 206.
So it is finally it's coming as 206 mod 210, right?
Yeah,
And notice that the product of 5, 6, 7 is mod 210.
yes.
Do you understand? In
Yeah,
all the questions that we have solved so far, finally it comes as product of the mods of these, right?
yes.
Okay, so now we'll state the statement of the theorem. We know how to use it. We'll state what it says. So Chinese remainder theorem says that uh, let's say you have a system of given pairwise coprime numbers n1, n2, and so on till nk, and arbitrary integers a1 to ak, a1, a2 till ak. The system of congruences x is congruent to a1 mod n1, x is congruent to a2 mod n2, and like this x is congruent to ak mod nk. Notice that the theorem is applying to pairwise coprime numbers. Okay,
What
so
does pairwise mean? Like in a pair?
yes,
Okay.
any pair of them is coprime.
Yeah.
So for example, 5, 6, 7, any two of them is coprime with each other.
Yeah.
So you are applying Chinese remainder theorem when you have a system of congruences which are pairwise coprime. The moduluses are pairwise coprime,
Yeah.
right? In that case, the theorem says that this type of system has a solution, and the solution is unique modulo the product of all of these coprime moduli. Okay.
Okay.
So this type of system has a solution, and the solution will be unique modulo this number. This number can be given capital F, which is the product of the modulus.
Yes.
So far in all questions, that's what we are getting.
Right.
Finally, the answer is coming as a number that is modulo 210 or modulo 105 we got, right?
Yes.
So as long as it is pairwise all of these co-prime numbers, then it will have a solution, the system. And the method of solution is the same that we have been using, okay? But there is a formal process also, general construction, which I will tell you. If you are confused by it, don't worry about it so much. You can use the same method you have been using. But you can also try to apply that method and see if you can get it from that method, okay? Because so far what we have been doing is like a step-by-step process, but it is limited because if there are 3 or 4, you can do it. But if there are 10, what will you do, right?
Right.
Do you understand what I'm saying?
Yes.
The process that we are using is the same thing, but it is a little limited because it's a stepwise process. We want to get a general method which can solve any number of congruences directly, right? So
Right.
what we'll outline is an algorithm that will do the same thing that we have been doing, but in a more systematic way, which doesn't require you to keep doing it like that, one by one, right?
Yeah.
So the first step is, so our question is the same. X1 is congruent to A1 mod N1. X2 is congruent to A2 mod N2. Like this, till Xk is congruent to AK mod Nk. We have to solve this system. Okay. So the first
Yeah.
step is calculate the N1 into N2 till Nk. Right?
Right.
Our final answer will be congruent to that capital N only, right?
Yes.
So now the second step is for each Ni, calculate Yi is equal to capital N by Ni. Okay.
Yeah.
So basically that will be N1, N2, Ni minus 1, Ni plus 1 till Nk. Because you are dividing this capital N by the Ni, right?
Yeah.
Do you understand this step?
Yes.
So third step is for each I goes from 1 to k, for each I from 1 to k, compute Zi is congruent to Yi inverse modulo Ni, mod Ni. So I'll talk about what is the meaning of the inverse. So anytime you have a, let's say you have a 4 mod 5, right?
Yeah.
When you do mod 5, the possible mods are what? 0, 1, 2, 3, and 4, right? Okay.
Mm-hmm. Right.
There is a number, we can try to find out what is 4 inverse mod 5. So by inverse, what we mean is that what is 4 inverse? 4 inverse, let's say, is y. So y times 4 should be equal to 1 mod 5. Do you understand what I'm saying?
Yeah.
So basically, when you say two numbers are inverse of each other, usually you have to use A into B should be 1, right?
Right. Yeah.
So if 4 mod 5, I want to find the inverse of 4. So which number can we multiply with 4 so that final answer will be 1 mod 5? Think about it. So 4 is its own inverse
So 4.
because
Yeah.
4 times 4 is 16, which is congruent to 1 mod 5,
Yeah.
right? 4 times
Yeah.
2 is not working, right? 8 is 3 mod 5, right?
Right.
4 times 3 is also not working. 4 times 1 is also not working. 4 times 0 is also not working, right?
Yeah.
But 4 is working with itself, right?
Yeah.
So inverse is pretty simple. You just remember your normal multiplication. When you say A and B are inverse of each other, it means product should be 1, right?
Yeah.
So suppose I want to calculate inverse of 2 mod 9. 2 inverse mod 9, right? So
Yes.
think of all the numbers. What can we multiply with 2 to get a 1 mod 9? 5, right?
Yeah.
2 inverse is congruent to 5 mod 9.
Right.
Do you understand what I'm saying?
Yes.
So for each of these i's, what you have to find is you have already found yi, right?
Mm-hmm.
You have to find the inverse of yi, mod ni. Do you understand?
Yeah.
So basically find some zi such that zi times yi should be 1 mod ni, right?
Right.
And those zi would be the inverses of yi, right?
Yeah.
I hope you understand this step.
Yes.
We will look at the process and do an example with the process that should help us like know what exactly to do. So
Yeah.
the fourth step, and I think it's the last step. Yeah. The final step is find the answer. The answer is x will be summation I goes from 1 to k, and x will be finally ai yi zi. And this will be obviously modulo capital N finally. That will be your answer. Answer to the whole system of congruences, okay?
Yes.
So if you have followed the first 3 steps, you already know all the yi's and zi's, right?
Yeah.
And the ai's are anyway given in the problem, right? So
Right.
basically this is what? A1 y1 z1 plus A2 y2 z2 and so on. You have to add till ak, yk, zk, and this answer modulo n is your answer, modulo capital N. Do you
Yeah.
understand? So now
Right.
let's apply this method and solve the same problem that we did earlier, the first problem that we did. Okay.
Okay.
So the first problem was, I will rewrite it here only. X1 was congruent to 1 mod 3 and x2 was congruent to, first problem was stated in terms of x only, but ultimately we can call it 3 different variables. We have a common solution, right?
Right.
4 mod 5 and x3 was congruent to 6 mod 7. This was our first question, right?
Yeah.
So in the first step, what do? We multiply and find capital N. So 3 into 5 into, notice that they are co-prime, right? 3, 5, 7.
Yeah.
They are pairwise co-prime. So we get 3 into
Yes.
5 into 7, 105 as capital N, right?
Right.
Our A1, A2, A3 are known, right?
Mhm.
For each Ni, we will calculate Yi first, right?
Right.
So Y1 will be 105 by 3, right?
Yes.
So Y1 is 35. Y2 will be 105 by 5, so
Yep.
21. And Y3 will be 105 by 7, so 15, right?
Yeah.
Now is the main step, which is calculating the inverse of all of these yi relevant to their mod ni, right?
Yes.
So we have to find out 35 inverse mod ni was n1 was 3, right? And then we have to find out 21's inverse when you do mod of 5, right? And
Right.
then you have to find out 15's inverse mod of 7, correct?
Yes.
Okay. So 35's inverse we need, right? So what should
Yeah.
I multiply with 35 to get a 1 mod 3, right?
Right.
0 doesn't work, right? 35 into 1 doesn't work. 35 into 2 works, see?
Yeah.
35 into 2 is 70, which is 1 mod 3, right?
Yes.
So 35 inverse is simply 2, right?
Yeah.
So Z1 should be 2, right?
Right.
Z2. Now 21 inverse with mod 5, right? So 21 with 1 will work automatically, right?
Yeah.
21 into 1 is still mod 5, right?
Yeah.
So 21 inverse should be what? 1.
Right.
Do you understand what I'm saying?
Yes.
Z2 is 1 and Z3 is 15 inverse with mod 7. So again 1, I think, right?
Yeah.
Right? So Z3
Yeah.
is also 1. These are all mod 7, mod 5, mod 3, right?
Yes.
Now we calculate our final step. So final step is A1, Y1, Z1. So A1 was what? 1, right?
Yes.
1 into 35, Y1, and Z1 is 2, right?
Yeah.
Plus 4 into Y2 is 21 and Z2 is 1 plus 6 into 15 into 1, right?
Yeah.
So this is 70 plus 84 plus 90, right?
Yes.
So this is becoming 70 plus 90 is 160 and plus 84, 244 mod 105, right? So basically that is what? 105, that is 210 will go. So it will be 34 mod 105, right?
Yes.
210 will be same removed from here, no? When you do mod
Yeah.
1. So 34 mod 105 is coming, right?
Yes.
And remember in the beginning, we got that only.
Right.
From our process, the long process that we did, right? We got 34 mod 105.
Yeah.
Do you understand what we have done so far?
Yes, I understand.
So this method, I will just rub off the relevant. This method is general because now we don't have to like do a stepwise process, iterative process, one step at a time, right?
Yes.
Here we can do at once, we can do like a system of 9, 10, 12, 15 congruences also. Okay. But ultimately, it's the same thing that we are doing. Conceptually, it's the same thing. It's just that this is better for more complicated problems, right?
Right.
If it's a 2 congruence, 3 congruence system, you can do it by the old method only, right?
Yes.
But know this is the algorithm to apply Chinese remainder theorem. Okay.
Okay.
Have you written it down?
Yes, I wrote it down.
Okay, fine. So that is the idea of the remainder theorem. And we can do a couple more questions where we can see it in actual exams and all. So for example, there is a 2017 EMC problem. It says let n is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. And after that, there is 10, 11, 12. Like this, you keep writing numbers like this till 43 and 44. Okay. This is a 79 digit number. 79 digit number that is formed by writing the digits from 1 to 44 in order. So now the question is, what is the remainder? Remainder when n is divided by 45. What is the remainder when n is divided by 45? Okay.
Mm-hmm.
So see here, what we can say is when you divide something by 45, basically they are asking you what is x is congruent to what mod 45, right?
Yeah.
And if you remember, we can split this if we knew a1 mod 5 and x is congruent to a2 mod 9, right?
Yes.
Wasn't that a pair of co-prime divisors?
Right.
So if we can go do that, then by Chinese remainder theorem, we'll know the answer here.
Yes.
Do you understand? It's a slightly different way of applying Chinese remainder theorem, right? Like you need the final answer of that, but you need to find these two, right?
Yeah.
And then apply Chinese remainder theorem to get the answer. Because directly doing it mod 45 is going to be very difficult.
Right.
Do you understand?
Yes.
So mod 5, calculating mod 5 is obvious here, right?
Yeah.
A1, right? It is obviously 4 mod 5, right?
Yeah.
4 mod 5. The mod 9 might be slightly more tricky, right? So think about it. The sum of the digits. So when you divide by 9, how do you do? Sum of the digits, right?
Yeah.
So you have to do the sum of all of these digits and see what is happening here, right?
Right.
Correct. So
Yeah.
sum of the numbers from 1 to 44, right?
Yes. No, it's the sum of the digits.
So sum of what are the digits? Digits are 1, 2, 3, 4 till 44,
Right. Yeah.
right?
Right.
Think about it.
But that would be different from the sum of the digits, right?
No, it won't be. Think of it. Sum of the digits, if you do mod 9, see, what are the digits? 1, 2, 3, 4, right?
Yeah.
You go till 9, right?
Mhm.
Then you have to do 10, 11, 12, right? So
Oh, okay.
technically you have a 1 and a 0, right? 1
Yeah.
and a 1. And
So that's just 1, 2, 3, 4 again.
uh, like this, if
So
you keep doing, I feel like it will be just the sum of these digits. One second. Uh, Let me think for a moment. Uh, See, the divisibility rule of 9 is what? That sum of the digits of any number, if you do mod 9, that is
yeah.
same as the number mod 9,
Yeah.
right? So sum of the digits of n is same as the digits of n is the same as n mod 9, right?
Yeah.
I feel like Okay, so we can actually count how many times 1 appears, right? No, it will be
Yeah.
annoying to do.
Can't you
Uh,
just do like the sum of 1, 2, 3, 4, 5, 6, 7, 8, 9, like repeatedly until. Wait, no, you can't do that because that's different.
so what you can say is 10, 11, 12 till 18, right?
Yeah, that's 1, 2, 3, 4, 5, 6, 7, 8, 9.
1, 2, 3, 4, 5, 6, 7, 9 plus 9 many times, right?
Yeah.
Right. Every
Yeah.
group of 9 numbers we can say is this sum, but extra 9s are added, right?
Yeah.
Do you understand?
Yes,
So
I understand.
till 36 you can do the same thing, right?
Yeah.
And then from there 37 to 44, right?
Right.
Basically that will be missing that last 9, right?
Yeah.
Do you understand?
Yeah.
So this is just 1 plus 9, this is just 2 plus 9, and this is just 9 plus 9, right?
Right.
And anyway, we wanted to do mod 9, so those we can totally ignore, right?
Right.
So ultimately, it's like 1 plus 2 plus 9 many times, right? Plus
Yeah.
finally 1 plus 2 plus 8 till 8, right?
Yeah.
37 will be 1, 32, 38 will be 2, and 44 would be 8, right?
Yes.
So 1 plus 2 plus 9 and all is basically 9 into 10 by 2, right? So it's 45.
Yeah.
So remember that all of these repeated sums are divisible by 9, right?
Right.
So we just have to check what is happening to this, right?
Yeah.
So that will be 8 into 9 by 2. So that's also 36, right?
Yeah.
So this is also divisible by 9, right?
Right.
Do you realize that everything is coming divisible by 9?
Yes.
So finally we have figured out that this is 0 mod 9, right?
Yeah.
Great. Now that we know this, we can solve this congruence by our Chinese remainder theorem method now. Do you understand what I'm saying?
Yeah.
That will give me our answer mod 45, right?
Right.
Since this is a two-term congruence, we don't need to use that general method. We can do it directly. Actually, let's do it by both the methods and check whether the same answer is coming.
Okay.
So let's do our first method that we learned. So that will be x will be 9k, right?
Yeah.
And 9k you are going to put into this. So 9k is equal to 5j plus 4.
Yes.
Or we should write it like this. 9k is congruent to 4 mod 5. 4 mod 5. And I want to make a 4 plus 5. So this is 9 mod 5, right?
Right.
And then I can divide by 9 because co-prime. So k is coming as 1 mod 5, right?
Yeah.
So k is equal to 5j plus 1, right?
Right.
And x is equal to 9k. So 9 times 5j plus 1, right?
Yeah.
45j plus 9, right?
Yeah.
So 9 mod 45,
Yes.
correct?
Yes.
That is the answer. That is the correct answer also. But now we'll also do it by the method that we learned, the second method, okay? The algorithm.
Okay.
So these two are our A1 and A2, right? This is
Yes.
A1, this is A2. Our capital N is clearly 45, right?
Yeah.
The second step was to find the Y1 and Y2. So
Right.
Y1 is 9 and Y2 is 5, right?
Right.
And the third step was to calculate what? Y1 inverses, right?
Correct.
9 inverse mod 5, right?
Yeah.
And 5 inverse mod 9, correct?
Yeah.
So let's find 9 inverse mod. What should I multiply with 9? 9 ones are 2s are 18, 3s are 27, 4s are 36, right?
Yes.
4 is the inverse of 9, no, mod 5.
Yeah.
So Z1 is 4, right?
Yeah.
And Z2, it is the inverse of 5 mod 9. So 5
Right.
into 1, 5 into 2, right?
Right.
Do you understand how I got Z1 and Z2?
Yes.
Now our answer is simply A1 Y1 Z1 plus A2 Y2 Z2, right?
Right.
The summation step, last step. A1 is 4, Y1 is 9, and Z1 is 4, right? And A2 is 0, by the way. So that is 0, right?
Yes.
So this is becoming 144 mod 45, right?
Yeah.
So notice that 144 mod 45 into 3 is 135. That's
Yes.
the same as 9 mod 145, right?
Right.
I hope you understand what I have done.
Yes, I understand.
This general process also you should be comfortable with. It should not be like some I don't do know how to do it.
Yeah.
It's easy only. Okay.
Okay.
Because sometimes doing the step by step method might be too long. Okay.
Okay.
Is it clear?
Yes.
So that is the Chinese remainder theorem, and this was an AMC problem. There are some other problems also where, especially in the AIME, Chinese remainder theorem has been asked many times. So,
Uh-huh.
so you need to know it, and you need to know the theorem that it applies when you have a system of congruences where the moduluses are pairwise co-prime, right?
Yes.
And after that, you can apply it. And if it's a small system, you can do it by hand only. If it's a larger system, then you should use the general method that we saw.
Right.
Okay, maybe we'll do one more class for some problems and then we'll end the number theory section, at least for now. We'll work on something else. Uh, okay, that's all for now. The next class will be problems on all of this stuff only. So
Okay.
we'll continue with that in the next class.
Okay. All right. Thank you.
Bye.
Bye.